Welcome to Lesson 13F, Particle Concentrations, Part 2. We're going to introduce a few more terms, do a comparison between these two different kinds of diameters, and then I'll talk briefly about why we need particle statistical analysis when we have an aerosol. I have a review here of definitions, terminology, and equations. An aerosol is a suspension of particles in air, and I didn't mention this in the last lesson, but these are typically smaller than about 100 microns. Anything bigger than 100 microns falls down so quickly that it can't really be considered suspended. And that's considering densities that are about the same as water. If they're really light, then of course they can hang in the air for longer times. Mass concentration, we know what that is. And then number concentration is number of particles, and that's typically in units of millions of particles per cubic meter. The conversion between the two we gave last time. And then particle mass for one particle, this is the volume of a sphere, so it's just density times the volume. Mean particle mass, you take the average of all the particle masses, so we have this equation, and then we defined dPam based on mass, which is the arithmetic mean, that's what AM means, diameter of the particle based on particle mass, which is what this means in parentheses. So that's the equation for the volume of a sphere in terms of dPam mass and giving us this equation. These units are in microns, but you have to be careful when you plug in these values to make sure your units all agree. dPam diameter is simple arithmetic mean diameter based on particle diameter, so that's the simple average. By the way, MP mean is also calculated if you know the mass of each particle. You can do this summation and divide by NT, just like we do here. That's a simple mean also. Now, for a polydisperse aerosol, dPam mass is not equal to dPam diameter. In fact, dPam mass is greater than dPam diameter. And I'm going to do a simple example to show that. We have just 3 particles occupying a cubic meter that I illustrate in this table. The density of the particles is 1,000 kilogram per meter cubed. By the way, some people call this unit density, so I want you to remember that term, unit density. Sometimes I'll give you problems with unit density. That's the density of water, 1,000 kilogram per meter cubed. The wording comes because this is equal to 1 gram per cubic centimeter. And so that's where the term unity, meaning 1, comes from. In terms of our normal SI units, it's actually 1,000 kilogram per cubic meter. So I have these 3 particles. I just labeled them 1, 2, 3. They have micron diameters of 1, 2, 3. So it's very simple. I just made up these numbers. So I had to calculate the mass of each one of these particles separately. All I did was use MP as rho p pi dp cubed over 6. You can imagine a 1 or 2 micron particle has a really small mass, and these are in micrograms, and they're still 10 to the minus 7. I give a sample calculation here with unit conversions to make sure that you get that right. So this is what we're plugging in here, and then we repeat for the other 2 particles. I get these 3 masses. So these are the mass of each particle. So to calculate dPam diameter, it's the simple average of these 3. So 1 plus 2 plus 3 divided by 3. And so that just gives us 2. You can do that one in your head. Similarly, for MP mean, it's just the average, the simple arithmetic average of these 3 masses. So you add those up and divide by 3, you end up with MP mean equal to 6.2831 times 10 to the minus 6 micrograms. Now we can use the equation that I just showed you from last time. dPam mass is 6 MP mean over pi rho, the whole quantity to the 1/3. And you have to be very careful with the units. Notice that I put unit conversions in blue. I put one of them inside the brackets to get rid of the micrograms and the kilograms, and then I put the other one outside. So just be careful with your units. And if you do all that properly, you end up with 2.29 microns. Comparing these two, you can see that dPam mass is not the same as dPam diameter. In fact, it's greater, as we said. And that's because, like I said last time, when you calculate masses, your mass is proportional to dP cubed, whereas diameter is proportional to dP itself, just dP to the 1. So the bigger particles, like this number 3 here, this one has a much bigger mass and weighs heavily in the average mass. Now I want to do a few more definitions and terminology. These are terms that are used in the air pollution business. A cloud. What is a cloud? An aerosol volume that behaves as an ensemble or a collection of particles. In other words, the particles move together as an ensemble. That's just a collection of particles. Some examples are a puff of cigarette smoke that kind of just moves with the air and doesn't really dissipate much. It just kind of moves along like a cloud. And a cloud of water droplets, if you look up at the sky and there's a cloud, it seems to kind of move together. Dust is an aerosol of dry solid particles. So these are solid, not liquid, typically supermicrons. So dP is greater than 1 micron. That's what supermicron means. And some examples would be coal dust and powders like talcum powders. Fumes is an aerosol of submicron particles, typically small condensed liquid particles from liquids or molten metal. You have metal that actually vaporizes. It's hot enough to vaporize. For example, we're talking about things like welding. So when you weld, you can get vapors of the metal, and then it condenses into tiny liquid particles. And so that's called a fume. And I just want to comment that they may coagulate. So they're very small to begin with, typically less than a micron, but they may coagulate into bigger particles. And they also eventually they solidify. So you have vapor, condenses to liquid, and then they solidify into solid particles. A mist is an aerosol of liquid droplets, typically much larger, about 20 microns or more from water. Examples are atomized drops of oil from, say, an oil burner or a water spray bottle. Here's an example. I have a little spray bottle that I use to clean my glasses. And so when I spray it, I don't know if you can see that on the video, but you can see a mist that comes out. I usually bring that to class, but I'll just do it on video here. Smoke is an aerosol formed by combustion. You typically have condensed vapors plus other small solid unburned particles, and soot, which I'll define in a minute here. These are typically smaller than a micron when you have good combustion, but they do tend to coagulate into bigger particles. So for example, fires. Soot is an aerosol of particles that result from incomplete combustion of hydrocarbons. Remember, we talked about stoichiometric ratios, etc. So typically due to a lack of sufficient oxygen, in other words, fuel-rich combustion. Pyrolysis is another thing that produces soot. Pyrolysis is the technique where you burn not quite enough. It's very starved for oxygen, and where you turn wood into charcoal. That's a process called pyrolysis. A good example of that is diesel smoke, like I show here when you sometimes see on the highway where you get this big black puffs of smoke from trucks. Finally, smog is an aerosol of smoke and fog, so it's a clever combination of SM and OG to make smog. Didn't know if you know where that term came from. Typically due to combustion, also has typically some NOx, NOx. That gives it its brownish color. And then it also usually has ozone, and these are all typically in smog. Smoke, fog, plus these gases. Here's a picture of Los Angeles, and notice the temperature inversion that we talked about before. This is the stuff that I used to have to breathe every afternoon when I was at Caltech in grad school. So not very nice to breathe all of those particles. So that's what smog is. Finally, I'm going to give you a quick illustration of why particle statistical analysis is necessary. I'm going to consider two very extreme cases, case A and case B, of coal particles in a box of volume 1 cubic meter. So these are identical boxes, identical mass concentrations, but two very different particle distributions. In fact, these are very extreme cases. So the first one here, case A, has just one particle, and it has a mass of 0.01 kilogram. So CJ is MT over V, which is equal to the total mass over 1 cubic meter, and that gives us 0.01 kilogram per meter cubed, where MT is equal to 0.01 kilograms, since there's only one particle here. So we don't have to do any kind of total or anything. For case B, MT is 0.01 kilogram, but there's a million suspended coal particles. So MP of one particle is total mass divided by total number of particles. This is a monodisperse aerosol because all these particles are the same size. So MT over NT gives us 0.01 kilograms per 10 to the 6th particles. So MP turns out to be 10 to the minus 8th kilogram. So this is the mass of one particle. This is also equal to MP mean, because if you take 10 to the minus 8th and add it up a million times, you get 10 to the minus 2, which is the total mass. So that makes sense. And so that's also MP mean. This is a monodisperse aerosol. And then CJ, using the same formula we had up here, MT over V, gives us NT times MP mean over V. So this would be 10 to the 6th number of particles times 10 to the minus 8th kilogram. That's the mass per particle over 1 cubic meter. And that gives us, again, 0.01 kilogram per meter cubed, which is the same. In this case, here we have the same CJ, but vastly different conditions. And these are extreme cases, but the bottom line is mass concentration alone is insufficient to describe an aerosol. We're going to also need some kind of statistics. Let me just write out what we need here. To fully describe a polydispersed aerosol, we need, first of all, mass concentration, but that is insufficient. As I showed here, we have the same CJ in case A and case B, but case A and case B are vastly different animals here. By the way, in this first one, you can't even call this an aerosol because it's just going to fall to the ground. Very quickly, it's not going to be even suspended. It's such a big chunk of coal. But these little tiny particles can be suspended in the air for a while. What else do you need? You need some measure of mean size, for example, dPAM number or dPAM mass, which, as I've shown you, are not the same thing. You need some statistics about either size or mass distribution. For example, you might have 1,000 particles that are between 1 and 2 microns. You might have 5,050 particles between 2 and 4 microns, etc. You need some kind of statistics there. We'll discuss statistics later on in the course. And finally, we'll usually talk about spherical particles, but if you have non-spherical particles, you need some kind of particle shape. You need to know that. So what we'll end up doing is defining an equivalent spherical diameter of some sort. We'll have a couple different ones that we'll define later in the course, kind of like what we did in fluid mechanics, where we defined a hydraulic diameter for pipes that are not round. We pretend they're round and define a hydraulic diameter. We'll pretend these particles are round by defining an equivalent spherical diameter.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.